I was sitting in a window seat the other day, staring out at the wing, watching the rain streak across the glass. And I had this thought about how local weather feels. You know, it's either raining on my head or it's not. It's windy where I am or it's calm. It feels so immediate.
It is personal, yeah.
Yeah.
Do I need an umbrella, or is my flight going to be delayed?
Yeah, exactly. Or did I pack the right coat?
Mm.
But then I started digging into the stack of sources we have for today, this massive comprehensive guide to global climatology for professional pilots, and it just completely shifted my perspective. Because for pilots, they can't afford to see whether it's just rain or sun.
No, absolutely not. If you're commanding a heavy jet across an ocean, you aren't looking at a local rain shower. You're looking at the entire planetary machine.
The gears.
How all the gears fit together, yeah.
That's the feeling I got. They see these massive interlocking systems, high pressure, fighting low pressure for territory. It's like a game of Risk played on a global scale.
And that's really the mission for this deep dive. We aren't just talking about why it rains.
Yeah.
We're going to decode the invisible highways of the sky.
A global tour.
A tour, yeah. From the engine room of the North Atlantic, down to the hurricane factories in the tropics, across the massive Pacific, and then back to the obstacle course of Northern Europe.
And what draws me into this is that it finally explains the why behind things we just accept. Like, why is New York a freezer in January while London is just gray and rainy?
Even though they're at similar latitudes?
All right. Or why a puff of sand in the Sahara can end up, destroying a house in the Caribbean 2 weeks later.
It's all connected.
It's fascinating stuff. So let's open the map. Where are we starting?
We have to start with the heavy lifter, the North Atlantic.
Okay.
This is the bread and butter for Western aviation. And climatologically, the North Atlantic is really a story of a wrestling match between two giants.
Right. Let's introduce the fighters.
In the north corner, wearing the blue trunks, you have the Icelandic Low.
The Icelandic Low.
It's this semi-permanent area of low pressure that sits roughly around 60 degrees north. It's the bad boy of the neighborhood.
The bad boy. So storms and wind.
Exactly. Low pressure means lifting air, which means clouds, storms, wind. The source material puts it at an average of about 1,000 hectopascals.
Okay, so that's the storm center up top. Who's fighting back from the south?
In the south corner, around 30 degrees north, you have the Azores High. This is the calm, subtropical neighbor.
Right. High pressure, nice weather.
High pressure, around 10 and 20 hectopascals, sinking air. Generally nice, settled weather.
So you've got this angry low spinning up near Iceland and this calm high sitting down near Portugal.
And the space between them is where all the action is. Think of the atmosphere like a fluid. Air wants to move from high pressure to low pressure.
They balance things out.
It's like water rushing down a hill. And because these two systems are so close and so strong, the air moves fast.
And then you add in the temperature difference.
Precisely. In winter, the Icelandic Low gets really deep and angry. The north is freezing, the tropics are warm. That temperature contrast creates what we call a thermal wind component.
Which gives us the jet stream.
That's it, the polar front jet stream. It runs right through that gap between the high and the low. It's the result of that pressure and temperature battle.
I think most of us know the jet stream exists. You see it on the weather map, but the numbers in this text were staggering. We aren't talking about a gentle breeze.
Not even close.
Yeah.
In winter, we're talking about core speeds hitting 200 knots at 30,000 feet.
200 knots, that's 230 miles per hour?
Yeah. Imagine your car doing 230 miles per hour, and then the road itself is moving that fast underneath you.
That's why flying to Europe in the winter can be so quick.
You're surfing a massive river of air. You can land an hour early, but if you're flying west,
You're swimming upstream.
you're fighting a 200-knot headwind, burning way more fuel, and the flight takes forever. That's the economic reality of these systems. It's not just weather, it's money.
Now, you mentioned the seasons. This engine changes gears in the summer, right?
The throttle's back, yeah.
Yeah.
The Icelandic Low gets weaker and shrinks. The Azores High sort of puffs up its chest and pushes north, sometimes up to 50 degrees latitude.
And that gives Europe better weather.
Pushes the storm track away, brings that nicer, settled summer weather.
Speaking of Europe and North America, I want to circle back to that tale of two cities idea because this has always baffled me. New York versus London.
It is the classic climatology question.
Okay, so let's look at the map.
Yeah.
New York is at, 40 degrees north. London is actually further north, up at 51.
Mm-hmm.
But in January, New York is often an icebox. Snow, frozen rivers. London is miserable, sure, but it's usually just rainy and above freezing.
It feels completely counterintuitive. You go north, it should get colder. But climate isn't just about latitude. It's about What is upwind of you?
So what's upwind of New York?
A continent. A huge, cold landmass. In winter, land loses its heat incredibly fast. The ground freezes solid, so the prevailing westerly winds are blowing over thousands of miles of frozen land before they hit the city.
The freezer door is left open.
Essentially, yes. The guide notes that the 0-degree isotherm, the freezing level, is right on the surface in New York in winter. You're living inside the freezer.
And London has the exact opposite setup.
Right. London has the Atlantic Ocean to its west. Water holds onto its warmth. It's like a giant hot water bottle. So the wind blows over this relatively warm bathtub of water before hitting the UK.
So London gets a heated blanket, New York gets a block of ice.
That's a good way to put it. In January, the surface temp in the UK is typically around +4 degrees Celsius. It's not tropical, but it's warm enough.
But that warm ocean comes with a catch. The guide mentioned a specific hazard called the fog factory.
Ah, yes, the Grand Banks, off Newfoundland.
That sounds terrifying for early aviators.
It's still a major challenge. It's a collision zone. You have the cold Labrador Current coming down from the Arctic, and it slams right into the warm Gulf Stream moving up from the south.
So you take warm, moist air and drag it over freezing cold water.
And physics takes over. The air cools down rapidly to its dew point. You can't hold the moisture anymore. It condenses instantly. Boom! Advection fog.
Not just a little mist.
No, thick, soup-like fog that can cover thousands of square miles. In early summer, it's basically a permanent feature of that part of the ocean.
A wall of white. Okay, let's leave the fog behind. Let's warm up and head south to the tropics.
The engine room of the atmosphere.
The guide spends a lot of time on the ITCZ, the Intertropical Convergence Zone. I feel like I learned this in school, but never really got what it meant for a pilot.
Think of it as the meteorological equator. It's not a straight line. It's this wandering band where the trade winds from the northern hemisphere crash into the trade winds from the southern hemisphere.
A head-on collision.
Exactly. When those massive air masses collide, the air has nowhere to go but up. And in the tropics, the air is hot and full of moisture. So as it rises, it explodes into massive thunderstorms.
So the ITCZ is basically a belt of storms circling the planet.
A belt of cumulonimbus towers, severe turbulence, lightning, and it moves. It follows the sun north in July, south in January. If you're flying across the equator, you're constantly watching the radar, picking your way through this wall of weather.
But the scariest thing in the tropics isn't necessarily the ITCZ itself, it's what the source calls westerly waves. Which I have to say the name confused me.
Ah, yes. The naming here is a bit of a meteorological headache. The text notes they're sometimes called westerly waves, but they're actually easterly waves because they travel from the east to the west.
Okay, let's stick with easterly waves then. What are they?
They're ripples. Ripples in the trade winds. They usually start as a little disturbance over northwest Africa. On a satellite map, they look like an inverted V shape in the clouds.
They sound harmless.
On their own, over the Sahara, they are. But they are seeds.
Seeds of what?
Monsters. The source material drops a really heavy statistic here. About 60% of Atlantic hurricanes and nearly all of the major intense ones start as these little ripples coming off Africa.
That is wild. A thunderstorm over Senegal is the great-grandfather of a hurricane hitting Miami.
That's the system. These waves move off the African coast, and if they hit water that is warmer than 26 degrees Celsius, they start to feed. The heat engine turns on. They organize. They start spinning.
And suddenly you're evacuating the coast. Wow. Now, speaking of the tropics, the guide pointed out a weird anomaly. Recife in Brazil.
Ah, Recife, yes. The exception that proves the rule.
Right, because usually tropical places have a wet summer, dry winter. But Recife gets its heaviest rain in its winter.
It's all about the local geography. The specific angle of the coast and the trade winds pushing moisture directly on shore. It's a reminder that local terrain always gets a vote.
And speaking of Africa again, there was another detail that surprised me. It mentioned Dakar, Senegal, having a visibility problem in winter that has nothing to do with water.
The Harmattan.
Even the name sounds aggressive.
It's a formidable wind. It's a dry, dusty trade wind that blows sand straight off the Sahara Desert, southwest towards the coast.
So planes can be grounded because the air is full of sand.
It's a sand fog, essentially. It can reduce visibility drastically. It's abrasive, dry, and it just coats everything in fine dust. You can be thousands of feet up, and the sky is just brown.
It really paints a picture. Let's hop over the Americas and look at the Pacific.
The Pacific Giant.
The scale is just hard to wrap your head around.
It's vast. And because the ocean is so big, the weather systems are scaled up. In winter, you have the Aleutian Low. dominating the north, just storm after storm churning away.
But the thing that jumped out at me was the speed again, the subtropical jet stream over Japan.
The strongest jet stream in the world.
The guide says it averages 130 knots, but often hits 300 knots.
300 knots. I mean, that is severe. If you are flying close to the core of that jet, the turbulence can be incredible. It's known as clear air turbulence, or CMTT.
You can't see it on radar.
Invisible. Because there are no clouds. And if you catch a ride on it, eastbound out of Tokyo, it's like being shot out of a cannon. But the difference in wind speed at the edges can rattle your teeth.
So you start in Japan at warp speed, and then you get to California, and things just stop. Specifically, the air stops moving. Let's talk about Los Angeles smog.
The famous LA smog.
I always thought it was just lots of cars. But the source explains there's a specific weather architecture that traps it.
It's a geography trap. It's caused by something called a subsidence inversion.
Okay, break that down for us.
So you have this massive high-pressure system sitting over the North Pacific. High pressure means air is sinking or subsiding. As that air sinks, it gets compressed and it warms up.
Okay, warm air coming down from above.
Exactly. But the air right near the cool ocean surface is, well, cool. So you end up with a layer of warm sinking air sitting on top of a layer of cool marine air.
Which is the reverse of normal.
Right. And this inversion acts like a physical lid on a pot. The vehicle exhaust, the industrial fumes, they rise up, they hit that warm layer, and they stop dead. They can't escape.
Then they just sit there and bake.
They marinate. The guide notes the worst time for this is September to January. It creates that brown haze LA is famous for.
And just up the coast, San Francisco has the opposite problem.
Advection fog again, just like Newfoundland. The Pacific High pushes air across the cold California current. It cools, condenses, and rolls right over the Golden Gate Bridge.
It's amazing how the same physics plays out. One more Pacific stop, Hawaii.
Paradise.
Usually. But the guide warns about the Kona storm.
This is the plot twist. Most of the time, winds blow from the northeast. The mountains catch the clouds. The north side gets rain. The south side, where Honolulu is, gets sun. Sometimes, between October and April, a low-pressure system develops to the west of the islands. This reverses the flow. The winds start blowing from the south.
And Kona means leeward, right? The sheltered side.
Right. So the lee side, the side that's usually protected and dry, suddenly gets hit full force with wind and rain. These Kona storms can bring 35-knot winds and heavy flooding to the parts of the islands that aren't built for it.
The invisible geography again. The wind shifts. The dry side becomes the wet side. Okay, let's bring it home. Back to Northern Europe.
The battlefield.
Europe seems tricky because it's caught in the middle. To the west, you have the wet Atlantic. To the east, you have something very different.
The Siberian High.
It sounds ominous.
It acts like it. In winter, a massive dome of high pressure builds over Russia and Siberia. It's just a pool of incredibly cold, dense, stagnant air.
And sometimes it decides to go on vacation.
If that high pressure extends west or links up with a blocking high over Scandinavia, it shuts down the Atlantic weather factory. It puts up a wall. The rain stops, but it brings in severe, biting cold and easterly winds.
This is when you hear about the Thames freezing over.
Exactly. It's a battle of air masses. Who wins? The moist Atlantic or the frozen Siberian block?
But the real headache for pilots in Europe isn't just the air masses, it's the ground, the Alps.
The Great Wall of Europe. Mountains mess everything up for pilots.
The guide details a few things here, but the one that stuck with me was the fun effect.
The fun. It's a classic example of thermodynamics in action.
Walk us through it.
Okay, imagine moist air hitting the south side of the Alps. It's forced to rise. As it rises, it cools. It dumps all its moisture as rain and snow.
So the south side gets soaked.
By the time that air crests the peak, it's dry. Now it plunges down the north side. As it falls, it compresses, and when air compresses, it heats up rapidly.
So you have this dry air getting hotter and hotter as it speeds down the mountain.
You get this strong, hot, dry wind rushing down the valleys.
Mm-hmm.
You can have a snowstorm on one side of the tunnel and clear, warm skies on the other.
That sounds pleasant, actually.
For a hiker, maybe. For a pilot, it means severe turbulence. The wind speeds can be dangerous, and the shift is just drastic. It shakes the plane around like a toy.
The mountains also create their own storms, don't they? The Genoa Low.
This is fascinating fluid dynamics. Air doesn't like to go over mountains if it can go around. So sometimes, as air flows around the Alps, it starts to spin on the sheltered side. It creates a vortex.
Like an eddy in a river behind a rock.
Exactly. A localized, intense low-pressure system spins up in the Gulf of Genoa. You can have fine weather everywhere else, but this one spot is stormy just because of the shape of the terrain.
Now, before we wrap up, I have to ask about icing. The guide makes a point that felt completely wrong when I first read it. It says clean air is more dangerous for icing.
It's one of the biggest traps in aviation meteorology.
Explain that. Why would clean air be worse?
It's all about how water freezes. To turn into ice, a water droplet usually needs a helper, a nucleus, a speck of dust, soot, something to latch onto.
Okay, so the dust tells the water, time to freeze.
Right. Now, maritime air coming off the pristine Atlantic is very clean. It doesn't have much dust. So the water droplets in clouds can get colder than 0 Celsius without turning into ice. They become supercooled.
So you have liquid water floating around at minus 10 degrees.
Exactly. It's on a hair trigger. It desperately wants to freeze. It just needs something to touch.
Like an airplane wing.
Precisely. The wing acts as the nucleus. The water freezes instantly on impact.
Flash freezing.
And it builds up fast. If the air was dirty, full of cotton dust, those droplets would have already frozen into ice crystals, which just bounce off. But supercooled liquid sticks.
So flying through that fresh ocean air is actually the high-risk zone.
It's a minefield if you aren't watching your temperature gauge.
We've covered a lot of ground today. The Atlantic engine, the tropical factory, the Pacific giant, the Alpine barrier.
It's a whirlwind tour of meteorology.
But the takeaway for me isn't just a list of facts. It's how connected it all is. You can't understand London's weather without looking at the Atlantic. You can't understand a hurricane without looking at the sand in Senegal.
It transforms the way you see the world. It's not just weather. It's fluid dynamics on a planetary scale. We are all living downstream of someone else's weather.
And for you listening, the next time you're on a flight and the pilot mentions a strong headwind or some bumps over the mountains, you'll know what's happening. You know you're fighting the Icelandic low or surfing a foehn wind.
You're seeing the invisible gears.
I want to leave everyone with one final thought. We talked about how 60% of Atlantic hurricanes start as these waves over Africa.
The classic butterfly effect.
It really makes you ask, in a system this connected, can a butterfly flapping its wings or a puff of sand in the Sahara really destroy a house in Florida? The science seems to say yes.
It makes you respect the atmosphere a whole lot more.
On that note, thanks for diving deep with us today.
Safe travels.
See you next time.